We have several different reasons we might want to subnet a large number of IPs. And we discussed this way back at the beginning of chapter 8. So you can see right here, we have a pretty large local area network with 400 users on it. And that creates a problem because of broadcasts. So with 400 users broadcasting things constantly, the network can become overwhelmed. So if we break that up into two smaller sections with only 200 users each, we reduce the number of broadcasts, in fact, in half per side of the network. So that's good. But when we talk about IPv6, there are other reasons to do it as well, having to do with the routing table. So the routing table is what routers use to get addresses from one side of the world to another. So if you think about how we go from our classroom to Google, we have to transmit over, I think we determined 7 or 8 different routers. Each one of those routers has to make a decision on how that packet gets to its next step. That decision is based on that routing table. And routing tables can be huge. In fact, on these big border routers on the internet, they are perhaps hundreds of thousands of lines long. So think of it kind of like a spreadsheet. So what I have here is a spreadsheet with different names on it, and these names are just randomized. So this might be a single classroom. For instance, Beth and Glenn and Grace might all be right here in my classroom. And for sake of argument, let's say it's Valentine's Day and somebody's coming in to deliver roses to various students. And so here are the students that they have to deliver roses to. Now, if these are spread out all over the building, Beth is perhaps in my room, and Glenn is in Mrs. Hawkins's room, and Grace is in Mr. Paul's room, then somebody delivering all these is going to have a heck of a time rolling all over the school, going from one classroom to another, and retracing their steps a lot. So it's going to be really inefficient. So what if instead we had a better way of organizing these students? So what we're going to do is say all students whose names begin with A through D are going to report to one room. And then the flower delivery person can simply go to that room and hand off all the flowers they have because they've been handed that list of students who start A to D. So if I just sort this, there we go, done. A through D. All of these students are now, let's say, in my room. And G through L, perhaps right here, are all in Mrs. Hawkins's room. So this is going to be a much easier way to manage people. This is essentially what IPv6 subnetting does for the internet. So here we have a list of addresses, and notice that they are largely just randomized. In fact, the last half of each of these addresses are randomized. But the front half has some things in common. So 1C65, here's another 1C65, and another, and another. So rather than saying, if you want to get to this address, you have to go to the Chicago router, and this address, you have to go to the, let's say, St. Louis router, and so on. So instead, we use these prefixes. We group them together, and we say everything that goes to a certain prefix is going to go to one router. So if we sort this data, now we have these nice groups. All of these first 4, all start the same way. So all of these are going to go to one router. These all start the same way. All of these are going to go to one router. Now, that means that we can eliminate the last half of these addresses when making decisions. We don't have to look at the whole thing. We just have to look at the first part and say, if it matches this, send it to Chicago. If it matches this, send it to St. Louis. And this is going to reduce our routing table. In fact, we go from millions or billions or quadrillions of lines down to only a few 100,000 lines, because these tables have to be stored in a router's memory, in RAM. The smaller they are, the faster that router can make a decision. So this is one of the reasons we subnet IPv6, so that backbone routers on the internet can handle all of those lookups.